Chapter 8. In Chapter 8, we discuss different techniques to solve the integrals, and it involves the basic integrals that you have already done at A levels or FSC. And then we had 8.2, which covers, I'm talking about the Thomas Calculus book. So for the 8.2, it covers the integration by parts that you might have done that as well in FSC and A levels. So I'm going to talk about the rest of the chapter, which includes the substitution, geometric substitution, and then the partial fraction method. So for the substitution method, for the geometric substitution, uh, remember that we discussed this table in the lectures, and we said that we discussed in detail why we have to use this particular substitution when we see something like this. For example, let's say the first case, we have under the root a square minus x square and use substitution x equals to a sine of theta. Once you do that, you should be ready to have dx equals to a cos of theta and the trigonometric identity cos square plus sine square equals to 1. So let's do a couple of examples. So the question might be like this. This is again from the book. I thought this is a good example for to solve. In this particular example, if you look at the denominator, we can clearly see that we don't have something a square minus just simple x square, but we have a constant minus a function of x, and that's a square. So this is similar to this one, the first case. Okay, don't get scared with the natural log of x. Again, if this is x or this is a function of x, it doesn't matter as long as you get something like this. This is it. So for this substitution, x equals to a sine of theta. You're gonna go with is the solution. Natural log of x equals to a sine of theta. A is 1 square here, so 1 sine of theta. So that's fine. Now to find the d of x, we differentiate both of them. For the left hand side, we're gonna get 1 over x into dx equals to cos of theta into d theta. So dx becomes x cos of theta into d theta. There are multiple ways to solve this, but I'm going to stick with the one that we discussed in the lectures. If you put back the into the integral that we had, we will get under the root 1 minus sine square theta divided by what we had x times. Remember that natural log of x, we took it equals to the sine of theta. So that will become sine of theta times d of x. D of x equals to x cos of theta into d theta. So the x cancels with this x, and inside the under the root we have 1 minus sine square, which is cos square theta. The square under cancels with the under the root, and we will have something cos theta into cos of theta into d theta. And in the denominator we have sine of theta. So for the cases in which we only have cos square theta in the denominator and there's nothing in the denominator, for the cos square theta d theta, for the integration, you can use the double angle identity, which is the cos square theta equals, we know, 1 plus cos of 2 theta divided by 2. And the integration of this one is very simple. The integral of 1 would be just the theta, and for the cos 2 theta, it will be just sine of 2 theta divided by 2. But here we got this sine of theta as an extra thing. So this becomes cos square theta divided by sine theta into d theta. Again, there are multiple ways to solve this. I'm going to go with the basic identity, which is 1 minus sine square of theta, because I know that I can cancel some of the terms and make this much easier to solve. If I now use the denominator, this is exactly equals to this thing, 1 minus sine of theta d theta minus sine square or sine, which is again just sine of theta into d theta. Now 1 over sine is cosecant theta d theta minus the integration of sine is again the cos minus of cos, so minus minus become plus cos of theta into d theta plus the constant of integration. For the cosecant theta d theta, we discussed a couple of times that you can do it yourself, otherwise just memorize the result and that would be enough. That is minus natural log of cosecant theta plus cotangent of theta. Sometimes some people like to put this minus on top of this one as a power, because this is this is a fundamental property of the logarithmic functions, that any power which comes before that can go there. So -1 can be on top of this one, but I'm going to go with this plus cos of theta plus c, and that's it. But remember that if you do the substitution, you have to do the back substitution as well, because we need the result in the form of x. That was our original variable that we start with. We don't want any u's or like thetas at the end in our final answer. So for the back substitution, we have to be very careful, because we did natural log of x equal to sine of theta. For the cosecant of theta, we know cosecant is 1 over sine theta. This is equals to the cosecant of theta. That means this will become 1 over natural log of x. So let's put this in the final answer as the back substitution. So 1 over natural log of x plus. For the cotangent, we know the cotangent is equals to cos over sine. The sine theta is again equals to the natural log of x. We know that. We did it in the first substitution. This is the only substitution that we made. So how are we gonna forget that simple thing? For the cos of theta, you can use again the basic identity. Cos square theta equals to 1 minus sine square, and then take the under root on both sides. So you're gonna get the cos of theta 1 minus sine square, and we know what is the sine theta. That is just the natural log of x whole square. Whole square, okay, not only on just on the x square, but the whole square. And what's left 1 over cos again. So 1 over cos, the cos theta is again the same thing, 1 minus natural log of x whole square under the root plus c. So I'm happy with this answer, but you can solve it further if you want. Similarly, let me change the color of the pointer. In one of the examples in the book, the question actually asks you to solve e raised to the power 2t plus 9, or e raised to the power 2x plus 9 or something. So we go back and look at this table. Now we have something similar here, a square plus x square, some constant, and the function of x. So we can do the same here. Just take this equals to, just treat it like this. We can just write down 3 square plus e raised to the power t whole square. Now see, this looks like the second one, a square plus x square, where we have to use the substitution x equals to a tan of theta. So our x becomes this. So we just used e raised to the power 3. A is 3 into tan theta, and then we solve it further. So this is another type of question in which we can use any method, but here we can clearly see that like integration by parts is not a good option to solve, because even if we go for this one, 4 minus under root x dot 1 over under root of x, and we take this one as the first one, this one as the second one, is gonna go, things gonna go very complex from here. If we go for the substitution, we don't know what to substitute. We are just sitting in the exam. So we try different things. First of all, we can try, okay, the first substitution. Let's try number 1, 4 minus x. How it will look like in terms of the d of x. So d of u equals to 4 minus x, 1 over 2 minus 1, okay. 1 over 2 comes here as well. And then the derivative of 4 minus x, which will result in -1 in times d of x. So if you do this substitution and you put back this here, you see that things will get very complicated and you will have no clue how to solve this. The second thing that comes to our mind is, okay, let's forget about the root, and we just put u equals to 4 minus x, because now things will become simpler. Du will result only in minus d power x. That's good. Now the integral will look like something like this. 4 minus x is u, so that will be just u under the root over under root x. times dx is minus du, so that's just minus du gets multiplied. Minus comes out. We have under u inside d of u, but the problem is the denominator, which is we have under root of x, and from this one we know that x equals to 4 minus u, and we will have okay 4 minus u. So you see that our problem hasn't been solved. We have now another integral which is a bit complicated, and there's no way to solve this. Let's do another thing. Substitute u equals to the under root x, and here we get du equals to 102. In fact, this becomes like this into d of x. Okay. Now when we do put it in the integral, our integral looks something like this. So if this equals to this, then the u square will be equal to x, right? So 4 minus u square divided by under root x, and dx from here that becomes 2 under root x into du. We like this under root x because it's going to cancel with this under root x in the denominator, and things will become very simple for us. So that's it. This cancels with this one, and you get an integral 4 minus u square. 2 comes out as a constant, and then dfu. So this seems to work because look closely at this table, and we have something where the first one where we have a situation under root a square minus x square, and we can just substitute x equals to a sine of theta, but you have to get ready for dx because it's going to result in cos of theta, and then we will use the derivative identity. Let's solve this again. So for this, we can use let u equals to 2 sine of theta. This means du equals to 2 cos of theta into d theta. This integral becomes 2. 2 will come out. We know that, right? And inside this, we will have left with 1 minus sine square, which is cos square. And du will be result in 2 times cos of theta d theta. So 2, and 2, all of them, they just go together, becomes 8. This cos square, this cancels with this, we will be left with cos square theta inside it into d theta. And like I discussed before, whenever you see cos of theta, you're gonna use this identity 1 plus cos 2 theta. Let's keep this 8 outside, okay? And you'll be left with, I'm just breaking it down, 1 over 2 d theta plus integration of cos 2 theta over 2 into d theta. So the answer becomes 8. 1 over 2 theta becomes theta over 2 plus cos 2 theta. The integration of that is sine 2 theta divided by 2. 2 times 2, and that's it. That's your final answer. But remember that we did the substitution of u equals to 2 sine of theta, not like u equals to 2 sine 2 theta. So we know what the sine theta is. We know that the sine theta is u over 2. But we have no clue about this sine 2 theta. So let's break it down. From here, okay, theta becomes sine inverse of u over 2. So we have to do this substitution again. Okay, so that means this will become sine inverse of u over 2 divided by 2 plus sine 2 theta equals to, let me add another slide for this. So sine of 2 theta equals to 2 sine theta, then cos of theta. And from our previous slide, we know sine theta equals to u over 2. So 2 multiplied by u over 2. For the cos 2 theta, like I said before, we're going to go with this identity, 1 minus sine square root theta. Take the under root on both sides, and you will get cos of theta. So this is 1 minus cos of theta is 1 minus sine square theta under the root cos of theta. And we know what is sine square, that is u square over 2, so u square over 4. So you will get 1 minus u square over 4. Once we put all of this here, okay, that gets divided by this 2 and then 2. We will have something like this. So the whole thing becomes 4 sine inverse of u over 2 plus 4 u over 2 under the root 4 minus u square over 4. The whole thing is under the root. So, but we know that we did one substitution as at the beginning, which was this one, u equals to under root of x, and we need the answer in terms of the x because that was the basic question in terms of the x. So let's put back the u. Let's put back the x, under root x, sine inverse of x by 2 plus 4 under root x by 2. And root 4 is just 2 in the denominator, so we will not care much about this. 4 minus under root x whole square. And the final answer becomes 4. You can solve it yourself by 2, the right hand side, but it just becomes 4 of x minus x square. And of course, in the final answer, we just include the constant of integration. That's our final answer. So we will have one more example from chapter 8. That is about the partial fraction. But in the exam, you won't know that if this has to be solved by partial fraction or something else. So you're gonna try different things. For example, if you look at it, this doesn't seem it will be simplified, but it will be evaluated by the integration by parts because you don't have two things to evaluate. And if you go for the geometric substitution, you can see there's nothing like this, any of these three things here in the question. If you go for a normal substitution, clearly it doesn't work. So let's find out. To use this is the most important thing to remember. If you want to use the method of partial fraction, you need to make sure that the polynomial should be the higher order than the denominator should be of the higher order than the denominator. So we need to convert it into proper fraction first. So for the proper fraction, we need to divide 9x cubed minus 3 of x, 3x plus 1. And then here we have that this is the divisor x cubed minus x squared. So we have to use basic division 9 times. So we get 9x cubed minus 9x squared. There is no 9x squared here, so we just write down here. When we subtract, we change the signs. So this gonna cancel. We get 9x squared minus 3 of x plus 1. And you can see that we cannot solve this further. So this is how we get the proper fraction. So this whole thing will become integration of 9 plus this 9x squared minus 3 of x plus 1, 3x, and then divided by x cubed minus x squared dfx. So first thing is to convert this into a proper fraction. Then we will solve it. For the 9, this is straightforward. 9 of d of x plus this one is 9x squared minus 3 of x plus 1 divided by x cubed minus x squared dx. This is simple. This will result in 9 of x. That is plus constant of integration, but we will try this later. Plus I, whatever this integration is. Now, if you look at the I, which is 9x squared minus 3x plus 1 divided by x cubed minus x squared, this is now in proper fraction, and we can now use the method of so 9x squared minus 3 of x plus 1 divided by x cubed minus x. So we have to use the method of partial fraction. How we do this? This is very straightforward. You know this minus 3x, you know the drill, how to do this. First, take x squared common from here, x minus 1. So for the partial fraction, we need to make fractions, but we don't know the coefficients. So These are the unknowns A, B, and C. So the first one is to the power 1. We just write it down simply like this. Now for the repeated roots, x square is repeated like x and x square. We write down with x1 for the first time b over x, and for the second time, as the degree of the polynomial decreases, we just write down c over x square. If this was x cube, we write d over x plus d over x cube with this as well. But here we will stop. Now, this is the trick to find the values of a, b, and c. First, consider all of this thing. Okay, the left hand side and the right hand side. We just want to get rid of the denominator, so we multiply everything by x square and x minus 1. What do we get? 9x squared minus 3x plus 1 equals a multiplied by just the x square, right? Because the x minus 1 will get cancelled by x minus 1 plus b times x minus 1 plus c times x minus 1. That's it. That is our main equation. Please remember that. We need to find the values of a, b, and c. The simplest method could be to put some value of x where we get only one of these variables and the other two cancels out or just becomes 0. So the easiest thing would be to put x equals to 1. And then we can easily see that the left hand side will become 9 times 1 square plus 3 times 1 plus 1 equals a 1 square. Why we choose this x equals to 1? Because we can clearly see here this is x minus 1, x minus 1. So if we choose the value, and there's no x minus 1 here with this a. So if you put the value x equals to 1, the terms with a b will become 0. The term with c will become 0, and we will be only left with a, and that is the easiest way. So plus b, everything will become 0 with this, and plus c, everything becomes 0 with this. Now we get 9 minus 3 plus 1 equals a. So the a becomes 9 minus 3 is 6 plus 1 is 7. However, there's now for the b and c, you can clearly see there's no other value of x that we put, and we cancel out a and c and get the value of b. So we go for the method of comparing the coefficients. Let me add another slide with this as well. Let's find out the value of a and b altogether, like with the method of comparing coefficients. So method of comparing coefficients. Okay. So if you want to compare, we look back at the equation number 1 and we just multiply everything together. On the left hand side, we're gonna get the same thing again, 9x squared minus 3x plus 1 equals. Multiply everything and you will simplify the equation like this: a plus b with x squared plus minus b plus c with x, and nothing with the x0. So when you compare the coefficient of x squared, on the left hand side is only 9. On the right hand side, you have a plus b. So we get equation number 1. Now compare the coefficients of x raised to the power 1. On the left hand side, what is with the x raised to the power 1? Minus 3. Okay. On the right hand side, with the power x power 1, we see minus b plus c. Okay. And sorry, this gets multiplied by the c as well. And comparing the coefficients for x raised to the power 0, we get 1 equals to minus c. So here we can clearly see c equals to minus 1. And once we put that value in this one, we get b equals to 2. And once you put b here, you get a equals to 7. So that means that our integral, which was actually this one, 9x squared minus 3x plus 1 divided by x squared x minus 1, is a divided by x minus 1 plus b divided by x plus c divided by x squared. Okay, we have done nothing but to put, we have just put the values here. That was our our main equation. We are just putting the values of a, b, and c and solving the integral. So things that becomes very simple for us. We know that the derivative of x minus 1 exists in the denominator, so it will become natural log of x minus 1 plus 2. Again, this has become natural log of x because the derivative of the x exists in the denominator. The integral of 1 over x is natural log of x plus. For this one, we can easily solve this by taking it to the denominator with x raised to the power minus 2. The minus 1 comes out, and this becomes the integration of this becomes minus 2 plus 1 divided by minus 2 plus 1. So all of this will result in plus 1 over x. So this is the final answer. And if you remember that the main question also had this 9 of x with it, so the final answer should has, okay, the final answer, if I write down, final answer, we should have 9 of x plus all of this together. So thank you very much. And if you have any other questions, just contact me, or we can discuss it later in the lecture. Thank you very much.